Well, okay. This is our last lab video before we start the new chapter and the new lectures and the new videos on acid base. So that's going to be next week. So before we do this lab, you have to understand this. Double replacement. So we're going to go over one before we do the one that's found in your lab. So here we go. The two substances, now remember everything goes back to bonding, the two substances we're going to use. Number one, it looks like this, and it's sodium phosphate. And the second substance we're going to use looks like this, and this is copper 2 sulfate. Now, before we even figure out how to do a double replacement, we got to talk about these two substances. Remember, if it's a substance, it's either going to be an element or a compound, and that means it's going to be homogeneous. So, look at sodium phosphate. Remember my rule for bonding. Anything hooked to a metal has to be an ionic compound. And if it's an ionic compound, it's a crystalline solid, like this. Here's a crystalline solid. The common name for an ionic compound is salt. So we have sodium phosphate and we have copper 2 sulfate. The sodium phosphate looks like this, a white crystalline solid. The copper 2 sulfate looks like this. It's blue. But you all remember why copper 2 sulfate has a color, because copper is a transition metal. Okay? Now, we got to put these together properly. And don't forget, the sum of the oxidation states have to equal 0. Right? Okay, so sodium, Na. Now, its oxidation state is +1. That means it wants to lose one electron to look like the electron configuration of a noble gas, group 18. Remember, all elements want to look like group 18 to be cool, electron-wise. So, phosphate. It ends in ATE. It is not a binary or a two-element compound. If it ends in ate or ite, it's a polyatomic ion. So, phosphate, PO4 minus 3. Now, I like to do it this way, some teachers don't, but if you detect there's a polyatomic ion, I want you to put it in parentheses, because when you balance one of these giant double replacements, it's easier to balance. So I'm going to go like this. Now, sodium wants to lose one, but phosphate wants to gain 3 to become stable. So all you have to do is crisscross and drop the signs. So that 1 is there, you don't have to put it because you know you have one of them. You're going to put a 3 there, like that. So that's sodium phosphate. Now, copper is Cu. The Roman numeral 2 doesn't mean take the second charge down. It means whatever the Roman numeral is, that is the oxidation state. So if it's copper Roman numeral 1, it's a +1. If it's copper Roman numeral 2, it's a +2. And then sulfate. ATE, got to be a polyatomic ion. SO4 minus 2. So look at that one. That one is a +2 and a -2. You don't need to do anything with it. That's it. The sum of the oxidation states equals a 0. So we're good with that. Now, these are solids. But in the double replacement reaction, we want to make them in a solution. Before we do that, bonding is everything, like I said before. When a metal is hooked to a polyatomic ion, and a metal is hooked to anything, it's ionic. But there's a second type of bond in both of these. So it's not only ionic, it also has a covalent bond due to the polyatomic ion, phosphate and sulfate. All right, so there's two types of bonds in here. There's an ionic bond, the whole thing is an ionic compound, and then there's a covalent bond in there. Now, when we put them in water, they dissolve. And now those two are called solutions. The reason that will make a solution and that will make a solution is because if you look on your reference table F, sodium hooked to anything is soluble, will dissolve. And copper sulfate, sulfate and copper, that will dissolve also. Even though sulfate has a couple metals that will be insoluble, copper is one that's totally soluble in there. Okay? Okay, so now I would have to put this. I don't need to, but here's what happens. You know now if you see AQ that it's a solution. And remember, solutions are homogeneous mixtures and they can't be filtered. So we have sodium phosphate added to copper 2 sulfate. All right? Now, okay, so I have rewritten this stuff. Here is the word sodium phosphate and copper sulfate. Here are the formulas. Now, to do a double replacement, you just flip-flop the two positive ions. That's all. So sodium is positive and so is copper. Flip-flop them. So the names would be sodium sulfate and copper 2 phosphate. So we're going to write them right here. So that's how you do the names, and the compounds is almost just as easy. So sodium sulfate, well, there's Na, and it's got a +1. Now, this is where a lot of people screw up. Do not take this 3 over to the other side, because that 3 is a crisscross product. Don't take it over there. So sodium is hooked to sulfate. Here's sulfate, SO4 minus 2. Now, that's a +1, that's a -2, you got to crisscross. So that's Na2SO4 plus copper Roman numeral 2, right there, copper Roman numeral 2 phosphate. Cu plus 2, PO4 minus 3. Obviously, that doesn't equal 0. Crisscross. So that 3 goes here, the 2 goes here. Now, one more time, you bring over the numbers if it's hooked to a polyatomic ion like that 4. That's 4's there, and this 4, that 4's there. Don't bring over crisscross products like that 3. Everybody got that? So we're all good right now. Now, the next thing we're going to do is we have to find out if the two products are soluble or insoluble. We know that this reactant's soluble because it has sodium in it. We know this reactant's soluble because sulfate's always soluble if it's hooked, except for a couple different things. Doesn't include copper. So we know for a fact sodium and sulfate, sodium's in there, totally soluble. Now, we have to look up copper 3 copper 2 phosphate. We got to look that up to see if it's soluble or insoluble. So on your reference table, phosphate is way over on the side where just about everything is insoluble. So when you look up phosphate, the only things that can be hooked to phosphate that would make it soluble would be a group 1 metal or ammonium. That is not a group 1 metal, that is not ammonium. So this is insoluble. So what I do is go like this. Drop an arrow down like that. That means it's insoluble. And it's going to fall out. And there will be a reaction. Now, we have to balance this equation. And I know people hate to balance equations, but double replacements are really, really easy. You balance by the polyatomic ions. Don't break them up. So let's start with something like this. Let's go with sodium. Look at, there's 2 sodiums there, and there's 3 sodiums there. The least common denominator is 6. So I have to put a 2 here to make 6 sodiums. I would have to put a 3 here to make 6 sodiums. Now, that 2 blows through everything, so now I have 2 phosphates. But I already have 2 phosphates. So look at, I have 3 coppers. So I have to come over here and put a 3 right there. But now, that 3 blows through everything, so I have 3 coppers, 3 sulfates. Well, guess what? There's a 3 there, it blows through everything, I have 3 sulfates. Everything's balanced. So that's what it looks like, the sum of the oxidation states, the sum of the coefficients. 2 and 3 and 3 and 1. So I have 5 over here and I have 4 here. Okay, so that's the sum of the coefficients. Sometimes that's on a Regents question. Now, the next thing we haven't done. We have to break everything up that breaks up. So this is soluble, that'll break up. That's soluble, that'll break up. That's soluble, that'll break up. This is insoluble. It has to stay together. So watch what we do. This breaks up into 6 Na plus 1 ions. 2 times 3 is 6. Plus 2 PO4 minus 3 ions. Plus 3 copper plus 2s. And then we blow through here 3 sulfates. And then we're going to go yields. So we have 2 times 3, we've got 6 sodiums. We have 3 sulfates. And remember, that doesn't break up. This does not break up because it's insoluble. So we go plus Cu3PO4 2 with an arrow down. So now it's all broken up. Now let's check and see if we did it right, because we should have the same amount of ions and substances on the same side. 6 sodiums, 6 sodiums. 2 phosphates, 2 phosphates. 3 coppers, 3 coppers. 3 sulfates, 3 sulfates. Perfect. So now what we have to do is cross off the ones that look identical. 6 sodiums, 6 sodiums. Let's see, sulfate, 3 sulfates, 3 sulfates. So now what we have left is what finally reacted. So we know that 2 PO4 minus 3s combined with 3 Cu plus 2s to make Cu3PO4 2, arrow down. This is the only thing that reacted. The 2 PO4s and the 3 coppers made that. Well, what about these other things like the sodium and the sulfates? What did they have to do in the equation? Well, this is pretty interesting, actually. So let's say you're 15 years old, you're on the basketball team, and you can't drive to the game. So your parents drive you to the game, all right? They go up in the stands and watch you play. So you're reacting, but they are spectators. What was their function? They brought you to the game. Same thing here. Sodium and sulfate brought phosphate and copper to the game. They reacted. So what the heck would sodium and sulfate be called? They are called spectator ions because they brought in what was reacting and then they sat back and watched it. They had nothing to do with the reaction. Okay? So here is the real reaction right here. And that's how you do a double replacement. So now we can start the lab. Okay, so now here are the two substances we're going to use. Well, they're called solutions because we already have them in water. All right? This is potassium thiocyanate right there, potassium thiocyanate. Notice it's clear. Yes, it's clear because it has no transition metals in it. The second one we're going to use, Iron III Nitrate. Not clear, colored because iron is a transition metal. So, what I want you to do right now is you should stop the video, put it on pause, and figure out what the two word products are over there. All right, stop the video, write the two word products, and then what I want you to do is figure out potassium thiocyanate's chemical formula, Iron III nitrates, and the other two. This should take a couple minutes, and obviously you're going to need a separate piece of paper to write this down. All right? Do that right now. It'll take maybe 5 or 10 minutes. Okay, so now I'm going to do this. Hopefully you've already stopped the tape and have done it. The word products are potassium nitrate, and Iron III Thiocyanate. Sorry, thiocyanate wouldn't fit, so I kind of misspelled it. Now, those are the word products. The next thing we got to do is we have to find the chemical formulas. Potassium, group 1, K plus 1, thiocyanate, SCN. That's a -1. So guess what? That's perfect. Don't have to do anything. Plus, iron, Fe. Roman numeral 3 means +3. Nitrate, NO3, -1. So there is a +3 to -1. That's not going to work. So crisscross and drop the signs. There's a 3 right there. Yields. Potassium is right there, K plus 1. K plus 1. Nitrate, NO3, -1. Another perfect compound, +1, -1. Plus Fe plus 3, SCN, -1. That's not perfect, so we have to crisscross. There's a 3 there. All right, now this one's pretty easy to balance compared to the one we just did. So let's look. I got 3 nitrates. Let's start there. 3 nitrates, well, there's only 1 there. So I'm going to put a 3 right there. That gives me 3 potassiums. So I got to come over here and put a 3. Now don't forget that 3 blows through everything, so that's 3 potassiums and 3 thiocyanates. But we already have 3 thiocyanates. We're all balanced. Okay? So, we know that that's soluble because it's got potassium in it. We know that's soluble because anything hooked to nitrate is soluble. We know that's soluble because it's got potassium and nitrate. We don't know about this one, Iron III Thiocyanate. And it's not in the solubility table. Thiocyanate's not in there. So the only way we can figure out if something is reacting is actually putting them together. And that's what we're going to do right now. All right, so now we are going to mix. The clear one is potassium thiocyanate. The colored one is the iron 3 nitrate. We're going to mix them together. Now, if we mix them together and we get a dilute color like this, then that's soluble. Nothing happened. But if we don't get that dilute color, then something happened. So let's see what happens. I'm going to pour the iron 3 into here. So something really happened, all right? And now, I call this the Dracula lab because this stuff looks just like blood, all right? But the problem is something happened, the color changed. So if the color changed, that must mean there's a chemical reaction, but nothing is falling out. This is a very weird thing going on here. Nothing is falling out. So there's actually no precipitate, all right? So here's what we have. We have to find out what the spectator ions are and what actually worked. Well, if this is the color of blood, then whatever hooked to this actually works. So, spectator ions. Potassium's a spectator ion, and nitrate's a spectator ion. So what actually worked in this double replacement? 3 SCN minus 1s plus 1 Fe plus 3 yields Fe plus 3 SCN minus 1, 3. That is what actually reacted. Now, what you're going to do now is this. On your paper, right here, for conclusion number 1, number 2, and number 3, I want you to write down this right here. 3 SCN minus 1 plus Fe plus 3 yields Fe plus 3 SCN. I want you to write that. That's circled right here for number 2 and for number 3, if you will do that right now. All right, so here we go. With the lab. Number 1 says pour FeNO3 into the first test tube. Here's FeNO3 right there. All right? Now, before we do that, do you remember that this stuff really didn't fall out? It was kind of suspended in there. So we're going to go like this. And remember what that means when you see the double arrow? That means equilibrium. So the rate of the forward reaction equals the rate of the reverse reaction, right? That's what it means. And do you all remember our little mound and hole thing? If you have an increasing concentration of something on one side, that's considered a mound, and it will shoot away from the mound to make everything equal. If you take out something or something drops out, that's a hole, and the reaction will fire into the hole. So, away from the mound, into the hole, or the other way, away from the increase in concentration toward the decrease in concentration. So, we're going to do our first one right now. If we take this Iron III nitrate and pour it into there, what would the common ion be? Think about that, because you're going to have to write it down for number one. What's the common ion? And would that be a mound or a hole? And if it's a mound, which way is the reaction going to fire? So before I do that, we're going to assign colors to these things. SCN, no transition metals. That's a clear color. Iron, that's a rust color. Iron III Thiocyanate, that's a blood color. Okay, so there are the colors, and that's going to be the key to which way the reaction fired. So you're going to have to write down, for number one, if I dump Iron III nitrate in this system at equilibrium, what is the common ion, which way will the reaction fire, and what will happen to the color? So here we go. I've lightened these up a little bit so you can actually see through them. So here's the Iron III. And if you said the common ion is the Fe+3, you're correct. So that's the common ion. There must be a mound there. The reaction must fire whichever way you think. Now watch. Pour a little bit in here. Did you see that? Look what's happening. Did you see the color change? There. That color really changed. So on question number one, you're going to have to write down why the color went dark red. Okay? Why the color went dark red. So that is question number one. And if you just want to write this on the email instead of taking a picture of the front and back of this picture, you can do that to me. But I want to know a good paragraph why the reaction got darker red when you put Iron III nitrate. Number two. Number two is we are going to put, if you turn the page over, we're adding potassium thiocyanate. So now you have to figure out which one is the common ion, where is the mound going to be, or the hole, which way it's going to fire, and what color would it probably change. All right, there's the KSCN. Here's the KSCN. Here is the Iron III Thiocyanate. Notice going down. Yep, it got darker. Not as dark as the first one, but it did get darker. So what you have to tell me for number two, and you can write it right on the back if you want, and then take a picture of the front and back and then send it to me. You have to tell me the same thing like you did for number one. What the common ion was, which way the reaction fired, and why the color got darker. Okay? Those are the two easy ones. The third one is a bonus, and it is difficult to understand. So here is what I'm adding. I am adding, and that's why I'm wearing glasses and gloves. This is your next chapter, by the way. This is sodium hydroxide. This is a base, and bases are, you can't really touch them, just like an acid. So this is a base, but notice NaOH, there is no common ion. Nothing in there has an Na or an OH in there. So I want you to watch and see what happens. I'll explain what's going on, but you look at the colors and see which way it fires. That's a hint to figure out what's going on. This is very difficult, and I'm afraid very few students are going to figure this out. But if you do, wow, good for you. All right, we're going to take this, which is Iron III Thiocyanate, and we're going to put some sodium hydroxide in there. Now, watch what happens to the color. That tells you which way the reaction is going to fire. All right? What's happening to that color? Color's almost gone away. All right, so that tells you which way the reaction fired. And I don't know if you can see it, but there's little teeny specks in here. And they're poured into a whiteboard, and now I think you can see the things that are falling out. Look. Hopefully you can see that that stuff is like a rustish colored, but remember I told you it's not a single ion that's falling out. It's something that combined together that falls out. And the key is reference table F. All right, good luck. For number 3, very difficult. There's no common ion. The reaction went from dark red to almost clear, and these little teeny specks of, they look rust-colored specks, are falling out of the solution. That's all I'm going to tell you. So number 3, you have to figure out what compound is actually falling out of this solution. And another hint is you should look on the solubility table, reference table F. Look on there and that'll tell you. So hopefully you'll be able, yeah, you can see, I can see these specks. I hope you can. Let's get a little bit closer, maybe you can see the specks. Okay, so that's the lab. You have 3 things. You have question 1, question 2, and the harder one, question 3. If you want to just write those 3 questions out on a piece of paper, take a picture and email me, that'll be fine. Or if you just want to send me the email with the 3 questions answered, printed out on the email, that would be fine also. This is your last lab and your last video before we go into the new chapter. Now, I'm going to start the new chapter probably on Tuesday or Wednesday. You'll get a new video. Okay? This is due Monday. And also what's probably going to happen is next week we'll all get on Zoom at a prescribed time, and I will use it for your questions on my video or videos on acid-base. That's how we're going to work it. So later on, we'll give you all that you need. But for right now, you get this lab. It's the last one in before the new material. And then I will produce my first video on acid-base. There's going to be a lot of them. And then we're going to figure out how to do Zoom, and you can ask me a bunch of questions there. All right? Good luck. Have a safe weekend.